Welcome to ProtoSign, a model for sign language recognition for low-resource languages created by Kavish Madhumal, Hasan Madhushan, and Dinet Vijaysurya, supervised by Dr. Tanuj Ambegoda and Dr. Sandareka Vikramanayaka. Before going in deeper, first an overview of the research. Let's start with sign language, which is a communication medium used by individuals who are hearing impaired, which consists of visual gestures and signs. None of those sign languages are universal, they differ from country to country, and are not mutually intelligible. In Sri Lanka, there are about 400,000 individuals in the hearing impaired community, and they find it difficult to communicate with the general public. Due to this, a communication gap exists between the hearing impaired community and the general public. So a sign interpretation tool like this SSL translator can help minimize the communication gap. But in order to develop such a tool, the available Sinhala sign language data is not enough. Due to this lack of data, we had to use a few-shot learning approach, which enables models to learn using a small number of examples, which makes this approach ideal for low-resource sign language. This approach can predict the class given a small number of support data and can be used in many applications like image classification, natural language processing, and speech recognition. So, what is the motivation for this research? By doing this research, our main intention is to minimize the communication gap and help the hearing and speech impaired community. And by developing this mobile application, SSL translator, we put this Sinhala sign-to-text translation capability in the user's palm. As our few-shot learning approach has been able to learn using a small number of examples, we hope our research will be a contribution in the domain of Sinhala sign language translation. Now let's take a look at the problem at hand. Currently, in the domain of Sinhala sign language translation, there exists no application developed so far to translate dynamic signs into text. And as you know, there are typically a low number of resources available in this domain. So our goal is to interpret this low-resource sign language. Now, let's discuss our objectives. In our project, there were three main objectives we had to fulfill. The first one is to implement a machine learning model which translates a low-resource sign language into text. The second one is to create the word-level Sinhala sign language dataset and make it publicly available. And thirdly, the third one is to develop a mobile application which facilitates this word-level Sinhala sign language translation procedure. Moving on, let's look at the literature review. In sign language datasets, there are two types of datasets, static and dynamic, and you can see examples of them in this table. Looking at sign language recognition approaches, there are four which are presented here with their corresponding papers. First, convolutional neural network is a type of neural network that is good at image processing, face recognition, and object recognition, but faces challenges in being much slower and requiring a lot of training data. Next, recurrent neural network is a type of neural network that can process sequences of data but faces a difficulty in generalization on new signs. Next, long short-term memory is a type of recurrent neural network that is good at processing sequences of data. And finally, transformer is an attention-based neural network architecture that is good at processing sequences of data. Looking at few-shot sign language recognition approaches, there are two. The first one, American Sign Language Recognition with metric learning-based lightweight network, is the proposed model that combines action recognition model training with metric learning, which allows the network to be trained on a dataset of limited size. And the other, skeletal-based few-shot sign language recognition, is the one researchers use where an LSTM model to generate vector embeddings and a GNN model for few-shot learning. Moving on to dataset contribution, our dataset is named as SSL50. In our dataset, there are 50 classes and 5 signers. There are around 22 videos per class and altogether 1,110 videos. These are the 50 words we selected. And these are some random video samples from our dataset. For the annotation, we use a straightforward pattern. The first 3 digits for word ID, the second 3 digits for signer ID, and the last 3 digits for same class, same signer, different background variation. Now we'll go through our methodology. First, an overview of our proposed ProtoSign framework. Starting from the left, we have the sign video. Then we extract the skeleton location of the person in the video for every frame. Then we generate the vector embeddings using a trained video encoder. Afterwards, we have the vector embedding of the video along with the prototypes for each class. A prototype is the mean value of a class. Then we calculate the Euclidean distance to each prototype from that vector embedding and take the class which has the minimum Euclidean distance as the predicted class. Now let's go through each part of our methodology. First, an explanation of the skeleton location extraction module. First, we have the sign video, which is used to generate the bounding box of the person using the YOLO V4 framework. Here we calculate the top left, top right, and bottom left coordinate values for each frame and crop the person from the video using maximum coordinates. After cropping the person, we extract the skeleton location using the media pipe framework. In that framework, there are two models, one for the hands and one for the body. Both models are employed here. Altogether, we extracted 57 skeleton locations, 21 per hand, 11 for the face, and 4 for the body. Now we move on to our sign video encoder. This is the training phase of the sign video encoder. Here we have the extracted skeleton locations. We send those skeleton locations to the transformer encoder. It creates the embedding matrix. We convert the matrix into a vector using the mean layer, which gives us the vector embeddings. Then we take 3 samples called positive, negative, and anchor. Positive and anchor are from the same class, and the negative is from a different class. We calculate the Euclidean distance between positive and anchor and the Euclidean distance between negative and anchor. Using those 2 distances, we calculate the triplet loss. Again, using classification head, we get the logits. Using logits, we calculate the cross-entropy loss. For the final loss, we use a combination of both losses. Here, beta is the loss mixing coefficient. The goal of our video encoder is to create the vector embeddings from the skeleton locations that cluster into the same class vector embeddings and generalize well to unseen classes. In our approach, we first tried the triplet loss with offline strategy for triplet selection. Then we use the triplet loss with online strategy for triplet selection. Finally, we use a combination of triplet loss and cross-entropy loss as the loss function. Here, LC is the cross-entropy loss, LT is the triplet loss. Beta is the loss mixing coefficient. We determine the optimal value for beta to be 0.9 from hyperparameter tuning. Now to the final part of our model. In the prototypical network, we have 2 datasets called support set and query set. Support set is like a training set and query set is like a testing set. Then we create the vector embeddings of both the support set and the query set. Then we take the mean value of each class in the support set vector embeddings to get the prototype of each class. These points are shown in the slide as points drawn in a vector space. The colored crosses represent the prototype. Let's assume that we want to predict the class of the query set. We calculate the Euclidean distance to each prototype from the query. Then we take the class of the prototype, which has the minimum Euclidean distance as the predicted class. Now let's look at the mobile application SSL translator. The main functionality of our application is to record the sign video and get a prediction. The application can live record a sign video, or it can upload a video from the gallery. Here we have limited live video recording to a maximum of 6 seconds to reduce the input video file size, while also not allowing users to upload videos from the gallery, which are more than 6 seconds. These are some of the screens from our application: splash screen, home screen, translate screen, and about screen. We can further see the functionality of the app via the demonstration at the end. Let's move into the results that we obtained during our research. We evaluated our protosign model against 2 low-resource datasets, SSL50, which is our proposed dataset, and GSLL, which is a Greek Sign Language dataset. We used a meta-learning-based approach to obtain the results. Here you can see the results that we have obtained for 1-shot, 2-shot, and 5-shot separately in 5-way and 10-way scenarios. You can see that in each scenario, 5-shot has the best accuracy. The accuracy of the GSLL dataset is better than the SSL50 because the GSLL dataset has static backgrounds. Moving on to the results of ablation studies, we conducted 4 ablation studies. First, we removed classification loss from the composite loss function and tested only with triplet loss. Inversely, we removed triplet loss and only tested with classification loss. Then we used a matching network instead of prototypical networks, and finally, we used another video encoder instead of the transformer encoder. These are the results that we obtained for SSL50 dataset. As you can see, the matching network has performed well in 1-shot scenarios, but in all other cases, ProtoSign model has the best accuracies. These are the results for GSLL dataset. Here, the ProtoSign model has performed the best accuracies in almost all the cases. Based on the above results, we came to these conclusions. By extracting the skeleton locations of the signer, we can achieve better results. Sign video encoders successfully generated vector embeddings, enabling effective representation learning of low-resource languages in few-shot learning scenarios. And the proposed model can be extended to translate other low-resource languages. These are some of the references that we used in our research. And finally, let's look at a demonstration.